Pedigrees and sex-linked traits. So pedigree charts are essentially a way of tracking inheritance through generations and looking at the family members from one generation to the next and tracking their characteristics. With these, we can determine if a trait is dominant or recessive or sex-linked or not sex-linked, and we'll talk about what that means in a second. They look something like this, where we have a generation here, and we'll look over all the symbologies in a second, but essentially we have a male and a female, and when they procreate, we draw a line between them, and then we draw their descendants down, and so this male and female had a son, a daughter, that circle there, another son here, which is a square, and another son here, which is another square. And then we show different things. So if the individual is affected with a particular trait we're talking about, we shade them in. If they're unaffected, we tend not to shade them in. And then there's some other more nuanced symbology that we use in this as well. So if they're deceased, we can put a line through it, that sort of thing. Here are some of them. If they happen to be identical twins, we link them together like that, or non-identical like that. Sometimes if they're carriers, we draw the shading taking up half of their circle or square, and we got the male and the female, and again their offspring are going to be coming out of that line between the male and the female. And then we are also able to label the generations, so we use the Roman numerals to label the generation, so that would be, say, generation 1, generation 2, and then we can label the individuals within there. So this would be the first individual from generation number 2 that we're talking about. This is the second individual, and if there's more, it'd be third, fourth, fifth, just so it's a quick way to write about what's happening in the pedigree without having to actually point to it. So let's take a look at this pedigree chart and see if we think this trait is dominant or recessive. If the trait is going to be dominant, then you know that you're going to see it in every generation, because if it's dominant, it will be expressed, even if the parent is going to be heterozygous, whereas if it's recessive, someone could be carrying that trait and not have the expression there. If it's recessive, then you won't see it showing up as often. So if we look at these two different pedigrees here, we can see that this couple here had 3 kids, and one of them had the trait, and then this couple here in the next generation down had 2 kids, and one of them had the trait. So it would be a recessive trait that we're talking about, because this couple here, neither one of them had the trait that we're talking about, but they were able to produce an offspring who had the trait. If it was a dominant trait, then one of the parents would have to have it as well. On the next one, we see that we have a parent here that has the particular trait, and they have a child that also has the trait. And here, again, we can sort of work backwards. So we say, okay, this child has the trait. One of their parents has the trait, who's one of their parents has the trait as well. So we can conclude that this is most likely a dominant trait, because we can see it showing up in every single generation, and it's going to be passed down directly. Much more occurrence within the pedigree as well. So say we take a look at this one here. Again, we have a couple that has 4 kids. One of those kids goes on to have 2 kids. Let's say we wanted to look at albinism. So albinism is a recessive trait. The shaded individuals in this pedigree here have albinism. The question we want to know is, what are the genotypes of these 3 individuals here? So take a look at the Roman numeral. That's the generation we're talking about. So everyone on this line is generation 2. Everyone on this line down here is generation 3. So we want to know the second person in, so that's 1 and that's 2. And the third person, this is the 4th person, and this is the 5th person on that particular generation. And obviously it's simplifying things, because having distinct divisions between the generations across different families is obviously not reasonable. But just for a simplistic pedigree, that's where we would be labeling who is which number on which generation. Generation 2, generation 1, generation 3 at the bottom here. This is individual 1, individual 2. And this is individual 1, individual 2 from the first generation. So the genotypes of number 2 from the second generation, what is their genotype here? And the third person from the second generation, what is their genotype here? And the first person from the third generation, what is their genotype? Now, if we're talking albinism, we have a recessive trait. And so if those individuals, which are the 3 mentioned here, if they have this trait, then they must be homozygous for that particular trait. So all 3 of those individuals would have, assuming we're using the letter A, recessive versions of those alleles and be homozygous for both of those alleles. What are the genotypes of the first individual in the first generation and the second individual in the first generation? So we know that the couple here produced 4 children. 2 of them had albinism, and so if they're both passing on the recessive gene, then they both must have that recessive gene. But since neither one of them themselves have the trait, they must be heterozygous for that recessive trait. Genotypes of the 4th person and the 5th person on generation 2. So these guys right here. And again, it's the same sort of deal. We've got 2 unaffected individuals, and they do produce an offspring who has the trait, so they must both have the recessive gene. However, both of them are not phenotypically expressing the trait, so they must be heterozygous as well. All right, oh, and there's the answer for the last one. If we fill in the remaining genotypes, we can't say for sure whether individual 1 on generation 2 or individual 2 on generation 3, we don't know for sure whether they're going to be homozygous. They could be, because they could have inherited both of the dominant traits from the parents, or they could have inherited one from one of them and one of the recessive ones from the other one. So they could be homozygous or heterozygous for this particular trait. Sex-linked traits. Genes found on one of the sex chromosomes, so either the X or the Y, but not on other chromosomes. We call those sex-linked because they're on the sex chromosomes. Mostly they tend to be found on the X chromosome because the X chromosome does have quite a bit more genetic information on it. And these traits are not equally probable between the sexes because a female has 2 X chromosomes. If it is an X-linked trait is recessive, then what that means is the female, if they have the X-linked trait, if it's recessive, they're going to have 2 versions of that particular chromosome, so they will not show the expression. However, a male only has 1 X chromosome, and so whether it is recessive or dominant, the male is going to express that particular trait. So females can inherit X-linked traits, males can inherit X-linked traits, and there are such things as Y-linked traits, just because males do have that Y chromosome. If there is a trait that is on that Y chromosome, then obviously males would be able to inherit it. The way these sex chromosomes works is different in different organisms. So we're used to talking about humans with the X and the Y chromosome, but interestingly enough, in birds, the male is the one that is homologous for the sex chromosome. Kind of like in humans, the female is homologous for the sex chromosome, but in birds, apparently the male is homologous for the sex chromosome, and the female, that's not spelled right, is a heterozygous for that particular sex chromosome. All right, take a look at those circles. What do you see? One of the sex-linked traits is called color blindness, and obviously color blindness doesn't mean the person can't see color. It's not like they're walking around seeing in black and white. What it means is that they have a particular change in their genes, and so they may have more difficulty differentiating between certain colors. And so there is one called red-green color blindness, where the individual cannot tell easily between those 2 particular colors. So if you're looking at those circles and you don't see the numbers in them, you may be one of the individuals affected by what's called red-green color blindness. This is what you should be seeing. These are the numbers right here. So you should see 25, 29, 45, 56, 6. I have trouble saying that one, and 8. So sex-linked genes, there's lots of genes on there, about 1,000 or so that are on the X chromosome. Most code for something other than female traits. So don't think of the X chromosome as being like the female chromosome, and the Y chromosome, the Y chromosome is the male chromosome. That doesn't make sense. The X chromosome has lots and lots of different genes on there. Many of these genes are responsible for things like hemophilia, muscular dystrophy, Fragile X syndrome, high blood pressure, red-green color blindness, as well as we saw with those circles. Some of these traits are going to be recessive and some of them are going to be dominant. So if it is dominant and a female is carrying that trait, she'll have that particular trait. If it's recessive though, she could be heterozygous and be carrying it but not express it. However, a male, because he only has one X chromosome, whether it's recessive or dominant, he will express the trait. So here is a dominant X-linked allele. So if we look at this, we have the father here who's unaffected, and therefore he's not carrying this particular trait. The mother who is affected, and we can see that it is actually red there. And so when these get passed on to the next individual or to the next generation, we have these 4 possibilities along the bottom here. One is that the father is going to pass on to his daughter. The father has to pass on his X chromosome, because if he passed on his Y chromosome, then that would be making a son. And so a father will always pass on his X chromosome to his daughter. The son, in either case here, is going to be getting the Y chromosome from his father. So whether or not they are affected or not is going to be depending on where they get their X chromosomes from. So a son is going to be getting his X chromosome from his mother. The mother has 2 versions of it. If the affected X chromosome ends up in the son, then he will have that particular characteristic because he only has one X chromosome, and this is a dominant trait. The X chromosome, if it gets passed on to a daughter, she will end up with it. And again, if it is a dominant one, then she will have that particular trait. But the other daughter over here has taken the other X chromosome and the other unaffected chromosome from the father, so she does not have that particular trait. So in this case, if it is an X-linked dominant allele, then there's a 50-50 chance of the offspring, whether or not they're male or female, of having that particular trait, assuming the mother is heterozygous for the trait. If it is a recessive allele, the mother is going to have the trait, but she is not affected by it. So we call her a carrier. So she's carrying the trait, but she is not affected by the particular trait itself. So this is a recessive trait. And what this means is that all of these couples' daughters will not be affected by the trait. One of them will be a carrier though, and the other one won't. And then in terms of the sons, the X chromosome is going to end up in the son from the mother, because you have to get, if you're a son, you definitely get your X chromosome from your mother. She has 2 of them. One of them is affected and one of them is not. And so if the unaffected one is the one that gets passed to the son, he won't be affected. If the affected one is passed on to the son, he will be affected. Y-linked disorders are less common because the Y chromosome has fewer genes on it, but the only method of inheritance is going to be passing directly from father to son, because every son gets his Y chromosome from his father. It's the only option. So if there is a particular trait on that, the son will inherit it from the father. All right, let's try practicing this. So hemophilia is a particular trait that is recessive on the X chromosome. So a female who is a carrier for hemophilia marries a normal man, and let's assume they plan on having children. Will their children have hemophilia is the question. So using the H for this particular trait, and we're going to look at the female. So she has 2 X chromosomes, and she is a carrier, as we said here, carrier for hemophilia. So what that means is she's got one allele that is the non-hemophilia allele, and then one allele that is the allele for hemophilia. The male is going to have a normal male, and again, by this normal, it's a bit of a judgment call is what you're calling normal, but he's going to be having, oh, that's a terrible Y, XY, and this is a X-linked trait. And so if this male doesn't have hemophilia, then he must have the non-hemophilia gene present, because he only has one X chromosome. So if he doesn't have hemophilia, then the only option is for it not to be on his X chromosome. So then we essentially set up a Punnett square between these two individuals, and we see that again, the female is going to be passing on her non-hemophilia X chromosome half the time, but also passing on the hemophilia chromosome half the time. The male is going to be passing on his non-hemophilia X chromosome all of the time. That's the only one he has, and then the Y chromosome. So these individuals here, if we look at them, we end up with a daughter who is going to be homozygous. She will not be a carrier for hemophilia, and a daughter that is a carrier for hemophilia. It's recessive, so she would not be expressing that trait herself. It would not be in her phenotype, but she's a carrier for it. They would also have a 25% chance of producing a son that does not have hemophilia, and a 25% chance of producing a son that does have hemophilia. And remember, it's not that these people would have 4 kids. It is just a 25% chance for each of these boxes on here. 25% chance of having a son with hemophilia, a 25% chance of having a son without hemophilia, a 25% chance of having a daughter who's homozygous without hemophilia, and 25% chance of having a daughter who is a carrier for hemophilia. All right, practice with some pedigree charts. So determine if the pedigree chart shows an autosomal or a sex-linked disease. So is this on their X and Y chromosomes, so it's sex-linked, or is it autosomal on one of their other chromosomes? So looking at this particular chart here, we see we've got 4 different generations, and if we look at the affected individuals, one of the first things that we should note is that they are all males. So that should tell you something as well. If it's being passed on, it's not showing up in every generation, and all of the individuals are male, then that's a good sign that it is going to be a sex-linked trait. And so if you look at the parents as well, so let's look at this individual parent, this male here on the 1, 2, 3, on the 4th generation. So the 4th individual on the 4th generation is affected by it, but his father does not have it. However, his mother does come from a father who has this particular trait. And then let's look at the 1, 2, 3, 4, 5, 6. So this is actually the 6th individual on the 3rd level here, was also affected by it. And he comes from a couple where neither the father nor the mother has this particular trait, but the mother's brother has that particular trait. So this is looking like a sex-linked trait in that it is only being carried by the males, and we can see that the parents are unaffected. So if we were to look at the genotypes of this male here, he definitely has it on his X chromosome because he is XY, so it is definitely on that X chromosome. And he got that X chromosome from his mother. So let's imagine one of her chromosomes also has the particular trait, the other one doesn't. She could have gotten that X chromosome. Well, she definitely got the X chromosome, one X chromosome from her father, and so if he had that particular trait, he would have passed that on to her, and so he's XY, and he's actually expressing that particular trait. And again, he got his X chromosome from his mother, who definitely has it, and then she's not affected, so she must have a this must be a recessive trait, because the mothers of sons who have it, the mothers themselves are not affected. So it must be a recessive trait, and then let's see if this makes sense in terms of how it can be inherited. So if this mother in generation 1 had the trait, she could pass on that X chromosome to her daughter, who would get a normal X chromosome from the father. And then if that X chromosome was passed to the son, he would have that as well as a normal one from his father here, and that would explain why he's affected. This father has an affected X chromosome and an unaffected Y chromosome, so it makes sense that he could also have offspring that are unaffected as well. He could pass on the unaffected X to the daughter, and then the Y and the unaffected X could end up in this son, whereas the Y and the affected X from the mother could end up in this son here. So a sex-linked disease. This particular one here, we can see just off the bat, we've got 3 females that are affected by it, 3 males that are affected by it. So it's less likely that it is going to be a sex-linked trait. And in terms of how it is being inherited, we can see that this individual here, the father in that generation, has the trait, and he passes it on to one of his children, the daughter here. And so again, if it was on the X chromosome, and let's say that is the Y chromosome, so we could say, okay, if it were to be X-linked, it would be on his X chromosome, because he only has the X chromosome. So this daughter would have got that affected one. So let's see if we can work this out here. And this mother here, she's got 2 X chromosomes. So let's imagine maybe it could be on her 1 X chromosome, and the father here with a X and a Y, who is unaffected by it. And if they pass this on to the next generation, this daughter here is going to be getting an X chromosome from the father and 1 from the mother. So if we know for sure she's getting an unaffected one from her father because he does not have the disease. So if this is sex-linked, it would have to be dominant, because we know that this individual here is heterozygous for the trait because her father is unaffected. And then this male here got a Y chromosome from the father, obviously, and the X chromosome from the mother would have been affected as well. So that so far is working out. This individual, let's go back to this generation and let me fill in the grandmother, is unaffected. So we know if this grandmother here is affected and this grandmother here is unaffected, then we know this has to be a dominant sex-linked trait. So far that is working out. This individual here would have gotten 2 X chromosomes, and again neither one can be affected. So when they produce a male, we'd have the X from one of them and a Y, but that doesn't work because this son here has to get his X chromosome from his mother, and he has to get his Y chromosome from his father. But this individual here has to, this person has to not have the trait, because if it was a sex-linked trait, it would have to be dominant. Otherwise, these other situations here wouldn't work out. So we can see through a lot of roundabout work that it does not work if this is to be a sex-linked trait. It worked for a little bit until we start putting it all together, and then we can say, okay, if this is a sex-linked trait, it looked like it had to be dominant, but then eventually we get to the point where that's not going to work as well. So it does not work to be a sex-linked trait. Even a dominant sex-linked trait does not work out in the end. So therefore, it must be a autosomal non-sex-linked trait. So, and again, you can quickly, the shortcut is quickly look for whether the males are affected more often. Then it's a good chance it is going to be a sex-linked trait. If it's a 50-50 ratio, it's a good chance it's going to be autosomal, not guaranteed, because again, you could have it work out in a particular way. If it's autosomal dominant, it might still work out. You have to go through and look at the possibilities based on who has it and what they have inherited. All right, let's try this one here. So just looking right off the bat, we see 3 males, they're affected with it. I would guess based on that, it's going to be sex-linked trait. But let's actually look at some of the details for it. So look at just starting with the bottom, and often it does work out well if you start with the most recent generation and then sort of work backwards through their lineage. So if you look at this son here, he is affected by it, and he comes from this couple here, and so he got his X chromosome from the mother and the Y chromosome from the father. And so if this is sex-linked, the X chromosome is going to have it. So let's just put a little dot there to represent that. And the mother could be carrying that particular trait there. She would have gotten her chromosome, her X chromosomes, one from her father. So let's imagine that she got that one from her father. And let's just imagine the mother has 2 unaffected chromosomes. Put a Y in for the father as well. So this is so far working out. If this X chromosome is carrying this particular trait, it could work out like so. And let's get rid of this. We can see that Y. So there's the Y. This particular individual here, again, this father is XY. If it is sex-linked, this father is not carrying it, because otherwise he'd be expressing it. So when he passes on his X chromosome to his daughter, which he has to do, she would definitely have one X chromosome that does not have it, and the other one could or maybe not, depending on whether it's recessive or dominant. If it is dominant, then we know for sure she must not be carrying it all. But it could be recessive, in which case she could be carrying that particular gene. So far, we've got to keep going and see what the data is telling us. So this X chromosome came from, let's go back to where we were. This affected individual here has one X chromosome, so if it is sex-linked, they would have that particular X chromosome with the trait on them. The X chromosome definitely came from the mother, because he would have got his Y chromosome from the father. So we have our XY here, and so this is a possibility for it being a sex-linked trait. Now let's check out the other side and see if it continues to work. So this generation 1 couple produced a daughter, of which she is getting 2 X chromosomes. One of them could have been the affected one, and based on the fact that this son down here has the trait, let's assume that that is the case, and this individual would be XY. So this son here does not have the trait, so he could have got, he definitely got his Y gene from his father, and then the X, so he could have inherited the normal X from his mother, but his brother would have got the X with the trait, as well as the Y from the mother, sorry, Y from the father, and the daughter here would have got an X from each one, and whether that is going to be dominant or not, we can't say. She could be a carrier for it if that's the one she inherited from her mother. All right, so far this looks like it could work out to be a sex-linked, again, because it's all males that are affected. This seems like a very plausible explanation that it is sex-linked, and in terms of the whether it's recessive or dominant, we know that this first generation, the father passed on his Y, and the mother created this X. So if it's sex-linked and the mother doesn't have it in the first generation, but she passes it on to her son, then it must be a sex-linked recessive trait. Otherwise, that original mother from generation 1 would be expressing the trait. And the fact that no other females are expressing the trait as well would lead me to believe that it is a recessive trait. So we could go with the X as a recessive trait on there, and I'm using a lowercase h to actually denote it. So we can actually go through, and let me clear this up so you can see it in nicer writing than my chicken scratch. There's your heterozygous mother in generation 3, and then we have the father who is affected by it in generation 2. And again, with the individual, the question is asking for all of their ancestors for this generation at the bottom, this person at the bottom here. So that mother there could be not carrying it all, or could be carrying it. We don't know for sure. And then, assuming this is a recessive, but it has to be a recessive trait, the grandmother would be a carrier for it, and the what is that? Father, grandfather, great grandfather would not have that trait with him.